Yay.
It's preparing the meeting. Let's see if it pops it up on my end here. It's always funny, there's like a little delay. All right.
And then you get to
There
hear
we
their
go.
voices.
Yep. I think we're here. Okay, good. We are up and running. I'm gonna bring up
Awesome.
I'm gonna bring up the feed here so I can see if anybody pops in the chat at all. Um, so anyway, all right. Here we are. Yeah, I wasn't sure if you guys pushed this on social media or not, but um
Yeah, we made a few posts.
Mhm.
well, looks like we have Jesse here, which is
In
good.
fact, I'm going to reshare it now on mine.
We're
I
gonna
love the name of the link, by the way.
what magnetometers?
What
I
magnetometers?
I will
It's
fix
a
it later. I
spell
can't.
check.
So yeah, when I create the Zoom chats, like I type pretty fast, so I will fix it. I will fix it in post, as they say. Yeah, if you
For
world.
everything.
Yeah. So anyway, so we're here.
Sounds good.
Live.
Hi
Welcome in.
all.
Welcome in. We're going to talk about magnetometers, but first we're going to go over current events, which there's not much of to speak of. Um, it's pretty quiet in terms of what was those? What did you call them? Theoretical CME.
There's like a slew of, I think, what, three, if I'm not mistaken,
Yeah,
that are all
two or
within like
three.
25 to 60% probability range,
Okay, yeah, so nothing
using
crazy.
Huxt at least.
Yeah, so we figured we'd just touch on it real quick, and in case anybody has any questions about it, just pop in the chat and we'll go over it. But we're gonna basically give the reins over to our friend Tanya, because we call her the Queen of Mags for a reason.
Oh my
And
God.
and
That is literally her title in our chats, just so
yeah,
everybody knows.
Queen of Mags is gonna take us through magnetometers, and hopefully we're all gonna learn something today, us, me included.
And me as well.
And me.
Me. So take it over.
All right, let me share this thing. So as Mary Beth already said, we don't really have a whole lot of activity going on, but there is definitely something popping up every now and then. We're still under the influence of high-speed streams, so we will see substorms here and there. And for that, our magnetometers, and we're going to talk about why you want or don't want to use one. So let's get started.
Rock on.
Everybody
Yay.
remembers Earth's magnetic field? Yay, it has magnetic field lines. And you probably remember the childhood experiment where you have a dipole magnet and a little bit of iron filings, and they settle down in a pretty picture, kind of pretty pattern along the field lines. Well, they do exist in space as well, and they are in 3D distribution. So they form what's called shells. It's sort of a 3D-like magnetic line that wraps around the entire Earth, like this over here. So that's one, two, and what's important to remember, and some of the schematics show that inaccurately, they have all of them converge at the north or south pole, and that's not the case. They do land somewhere else. They do close somewhere in the center of Earth. Well, not quite in the center of Earth, but they do go through the Earth core because they're formed by the core. It's a dipole field, so there is a south pole, which is actually north pole magnetically speaking, and there's north pole, which is south pole magnetically speaking. Why that is convention.
Yeah.
But it is the magnetic field of Earth, and the axis of that magnetic field is tilted toward the rotational axis, which creates a lot of interesting effects, which we're not going to go into, or at least for now. But this is a different presentation of it, and this is some neat experiments you can do with your compass if you have one. You can measure with the magnetometers, you can definitely measure the strength of magnetic field, and obviously closer to Earth, closer to the core, that's going to be stronger. And further away from the core, further away from the planet, it's going to be a little less. As a result of it, the lines that are closest to Earth have stronger magnetic field. Further away, they are weaker. It doesn't mean the entire magnetic field is weakening. It's just what the magnetic field strength is in certain position. And because it closes at certain latitudes, north and south, it's going to be equivalent magnetic field kind of all the way throughout, including on the ground, which is important for magnetometers. But you also have a declination and inclination angle. So what is that and why do you even care? The declination angle is how far magnetic pole direction in your location is away from the true north location. So that's the D angle. And the I angle is if you literally take a compass and instead of looking at it horizontally, you flip it and make it vertical, you can determine your magnetic latitude. That's going
Oh,
to be
I
the
know that.
inclination angle. Yeah.
Huh.
So that's pretty cool. Except the compass, conventional compass, is really not set up to measure the inclination angle really well. So it has a little bit of kind of tension and a little bit of inertia, so may not be entirely accurate. And that's why looking up your magnetic latitude would be a better idea. But yeah, your magnetic latitude is just your angle. So this is something that I expect all of you to remember for maybe about 1 second. But magnetometers measure the strength and direction of magnetic field. Every self-respected magnetic field has a direction, not just the strength. It kind of points in one way or another. And you can describe it in 3D space with angles and separate components. So you have the XYZ coordinate system. This is just geographic north and um, yeah, the east. And then you have the H and D and F and I and Z components. So Z component is the same, it's such as zenith. But H component and X component, there is an angle between the two, and that's your D angle, so declination angle. But they could be treated for aurora chasing interchangeably, because this is where you're going to see most of the effects of the current. But yeah, if you see magnetometers, they could be represented in THZ components or XYZ components. Don't let that scare you. It's pretty close. And you don't really have to do the conversion. If you want to, you can, but if you don't feel like, you just go with, mostly you're going to be using H and Z component. This is what we're going to talk about. So this is the intricate interplay between magnetosphere, so what happens in the magnetotail and what happens on the day side, and the ionosphere. And all those currents is what we definitely care about. But what we care about the most is one current system, and that's what we're going to cover. So just appreciate the complexity of the entire thing, and let's move on.
And next.
So
And this is super intense. And moving on.
Yeah.
yeah, moving to something that's fairly simple. So enter magnetometers, and particularly magnetometer stack plots. There are lots of them in auroral or high latitude, at least in the northern hemisphere. There are a few in the southern hemisphere, and there are a few that are at mid latitudes and equatorial. They all measure different things that are happening with magnetic field, obviously, and they do have a purpose, trust me, but you're not going to use all of them. We're going to use mostly auroral magnetometers, and this is my favorite charisma magnetometer array, church line in particular. So magnetometers are set up here from basically north to south. And this is very convenient line because it actually is along the same longitude. So they all going to change at the same time. What you see here is an average magnetic strength at that specific latitude where a magnetometer is sitting. So closer to equator, you're getting stronger reading. Further away, it's a little weaker, which is expected. So that's pretty normal. But this is a quiet day, not a whole lot of happening. Look at this, like, the more equatorward magnetometers are really doing nothing. They're just minding their own business and they're showing this wave. So why is it there if it's a quiet day? Because there is sun. and it's inducing some current in upper layers of the atmosphere, but those variations are fairly smooth, and all that minor activity, and that would be disturbed conditions or substorms or major geomagnetic storms, they are a lot greater than those daily variations. So most magnetometers do subtract it when they're plotted. So big variations will be taken out for you, and what you see pretty much is what you get. If you see some disturbances there, magnetometers will definitely register it. But it changes with season just a little bit because remember the Earth is rotating and the pole is going to bring it to slightly different points. So magnetometers will be sitting in a different position in relationship to sun during the daylight. And you're going to see changes in those curves. But I had to dig really hard to find a quiet day in magnetometers. It's
Yeah, I
not
remember.
easy to find nowadays. Just the wrong season for that. All
Yeah,
right. So this is what happens with a solar wind. So that nice and round deep hole, which is sort of like nesting donuts, so to speak, or nesting slinkies. I don't know, Mary Beth, if you have slinky, now is the time to bring it up.
I still have it.
Yay! Wrap it around.
Yeah,
This
like
is what you get. This is what you get wrapped around Earth for those magnetic field lines.
you
So,
can do.
and if you have one slinky and then you have another one nested right inside it, connecting to Earth at different longitude, different latitude, and it's slinky inside the slinky inside the slinky. But then you add solar wind to it. So solar wind will be stretching, it will be compressing the day side and stretching the magnetotail, particularly when it comes to south or negative BC. That tail is going to be stretched big time. But magnetic field lines, they don't mind being stretched. They don't like being bent. They don't like being reconnected. They don't like interaction with each other. But if you're stretching them, no big deal. Eventually, something else going to happen because you have two lines that are going in the opposite direction. Remember, they're still starting in that north slash south pole and going all the way into the magnetotail and eventually coming back and going into south north pole. So magnetically, it's sort of a closed system. They're closed magnetic lines until solar wind comes in. And that solar wind, if you remember, eventually it's going to stretch the tail to the point where the middle of it kind of starts to be on very, very shaky ground and starts to break. And that creates depolarization. So that current that's going across the tail and normally supposed to keep it intact, that breaks. So part of the tail is flung away as a plasmoid. So it literally is chunk of plasma that is separated from the tail and kind of goes toward, I don't know, the moon could be there, some other things could be there, but it is thrown away just to get the tail more stable. And the rest of it is slingshot to Earth. So you see those tiny things there? Those are the spacecrafts that are, GOES in particular, is sitting in geosynchronous orbit. So now that front, it's called depolarization front, is moving through GOES. So if you remember, we talked about GOES magnetometers, where initially you see the stretching of the tail. So you see magnetic field going down. And then once depolarization comes in, you see the uptick. You see the quick uprise in a quick rise in the reading. So this is what's happening in GOES magnetometer with the substorm. It basically feels all that flow of particles toward Earth. So where do they go, all those particles, and where do they connect? Because that's a lot of energy that has to be dissipated somewhere. That plasmoid that was discarded is just part of it. There is a second part that's coming in. So that actually gets connected to the ionosphere and forms a current. So upper layers of the atmosphere, they can conduct some electricity. There are particles that are flowing through, and that creates some interesting effects that magnetometers can pick up. So this is a current. Basically it's a current that's open, so there's no electricity flowing through it. And you have essentially a magnetometer that's just measuring the horizontal component of the magnetic field. And well, it's pointing to the magnetic north, no big deal. But when you close the current, and that's what happens with substorm, it's a current closure that happens in the upper layers of the atmosphere. All of a sudden, what happens? Deflection. So
Ah,
electricity, electrical current creates a magnetic field that will deflect the the compass and will be registered in magnetometers. So you can definitely see it, which is exciting because we can detect it. But with anything in magnetosphere and substorms, it's all about location, location, location. Where are you at in relationship to the current that's flowing? So what time, magnetic time, and how close you are to it will depend on what magnetometer will be able to tell you. Sorry.
you're fine. It's a
All
lot.
right. So this is what we see. So current closure happens with a couple of currents that flow out and into the ionosphere. So there's downward current and there's upward current and there is a current in between. That's basically is your aurora. It's even glowing green in the schematic, which is exciting. But that's called substorm current wedge because it literally just connects part of the tail, essentially. Um, and instead of reconnecting somewhere in the tail, all those lines are now connect in the upper atmosphere. This is what you can see in magnetometers depending where they at. So this is the center of substorm. This is the substorm onset point. They're probably looking at Canada. This is just my hunch because for us in Churchill line, 6 UTC is midnight. And substorms usually happen very close to midnight. They typically happen about an hour before midnight. So remember, we're talking about magnetic midnight. And that's the point where if you look through a magnetic pole at the sun, it basically is a straight line. So it's the opposite of sun as you're looking through the magnetic pole. So it's kind of weird because again, magnetic midnight is a place. It's also the time when you happen to be rotating through that point. So your local magnetic midnight may be very different, but your local magnetic midnight is the time when you are arriving at magnetic midnight of the auroral oval. Exciting. So this is what you can see, particularly in the H component. So remember, it's just horizontal component, and it's going to be reaction to that current. So you will see different types of deflections. And this is just for schematics. So let's say substorm happened at about 65 degrees magnetic latitude, and it's offset a little bit because its relationship to the geomagnetic pole. And I think I have a picture of that in previous slides so I can look at it if there are any questions. But you will see essentially some negative deflections in the H component, but you will also see some positive deflections there too. So this just to tell you will tell you where deflections are happening and if they're up or down. You'll see deflections in the D component. You'll see deflections in the Z component. Z is just zenith, whether or not it's pointing sort of straight up or it's still going down. But this is rather a complex picture, and it's going to be difficult to decipher sometimes from magnetometers exactly, and it depends on where you are. Now let's throw another wrench into the entire system. Magnetosphere does not rotate, but we are.
Yeah.
We are rotating under the auroral oval. So as you are looking at substorm in development, it is a rotating reference frame. So as you rotate, you will see different parts of the substorm, even if you are starting at the substorm onset. So let's say it's 2300, it's your magnetic midnight, and you rotated through it. You're going to continue to rotate as the substorm is doing its thing.
That's
And
pretty
you're going
crazy.
to see all the changes related to the substorm. Or you're going to rotate into it. If you're starting on the dusk side, if it's your evening and substorm just fired, you're going to rotate into it and you're going to see whatever phase of the substorm that the sun light will allow you to see, or location of the substorm will allow you to see, because you could be sitting further toward equator compared to where the substorm is, and you might see just basically the rays of it, the pink rays, or you may see more of a green. So that's gonna depend. That's gonna be determined on many different things. Is it helpful with all of that complexity? Is it helpful to know what substorm is doing? Yes. So let's compare substorms in ground
Yay.
magnetometers.
Look at
So
that.
this is a quiet day at Churchill Station. Nothing is happening. So same thing. It's February 3rd. That was a quiet day in the magnetosphere. But let's say, and I'm pretty sure this is what happened here, there was a little bit of southward BZ, and Christian can definitely check me on that one. But how do I know this? I see the growth phase. So the growth phase is when there is a connection on the day side. The lines are aligned, they're anti-parallel to each other. That results in magnetic line breaking on the day side and reconnecting in the back and kind of piling up in the back. Can you pile up forever? Not really. Sooner or later, you're going to get to instability. And this is probably what you're starting to see, that kind of instability before it finally breaks. So this is the growth phase, that kind of the hump in the beginning of it. And then it just basically tips over and pours all the particles in, and you start to see that current going in. So this is the expansion phase of the substorm. The current is established. It's definitely flowing. Do you want to wait until the end of expansion and see Aurora then? You're going to miss the best part. What
Fun
you want to
fact,
catch is
that
this
that was a
point.
negative BZ, and it was also a very sharp move to positive BZ after and right before it starts dropping.
Huh.
Yay!
Yeah.
Awesome. Classic. All right. Thank you so
So
much.
good
Appreciate it.
example.
Yeah. So you want to catch the beginning of the substorm expansion. You don't want to wait until it's in full expansion, because by that time you don't have a whole lot of particle flow. So a lot of color will be gone, and you're going to see um, recovery, which is basically literally recovery to the baseline. And that's when you're probably going to see some pulsating aurora, patchy aurora, diffuse aurora, kind of depends on where things are. But the show's over by the time, well, not completely over, but the best part of the show is over by the time it's in full expansion. So if you are sitting somewhere in a fairly dark spot and you wait for your magnetometer to go into expansion, and your magnetometer has been previously calibrated on all the variation due to sun and season, and the moon actually has been taken out of it, yeah, your personal magnetometer will be helpful. But otherwise, it's better to rely on something that's a little bit closer and has been calibrated to
Right.
a degree. What are limitations if you're going with a signet magnetometer? Well, it gets tricky. Local magnetometer may not be available, particularly the one that's been already calibrated, like the magnetometers in TGO or Charisma, CANMA. So there are several arrays. If they haven't been, if there is nothing that's locally available, you're out of luck. If you're looking at a magnetometer that's east, west, north, or south of you, you have to take that into account and kind of figure out what data in that magnetometer means. And remember, because H component varies depending on where the magnetometer is in relationship to the substorm current, you're going to be looking for negative deflection, but the magnetometer could actually be going positive for substorm in H component. And you're still going to be seeing aurora, but you're going to think you're going to miss it because magnetometer is just going in the wrong direction. So it gets a little tricky. It also depends, is a magnetometer you're looking at under auroral oval? So if it's seeing currents that are strong enough, or is it at mid latitudes where it will wiggle just a little bit? It still feels that current, but what you're going to see for it, because it's such a muted response, you're going to see a little bit of a positive rise in it, but that might be just about it. And you're going to miss the aurora because, again, it might be a substorm that's further closer to the pole, and you should be able to see the rays, but you're looking at the magnetometer and saying, well, nothing is happening. It's not interesting. So is it good to rely on local magnetometer? You can, but it's going to be problematic. You're going to probably miss a lot of stuff. Okay, so can we get better than the local magnetometer? Let's go with my favorite longitudinal line. So this is charisma, and this is the line that I use quite a bit to demonstrate what is happening in the magnetosphere, because it's pretty convenient. You can track what substorm is up to, where is it happening, how it's happening, again, to a degree. Because again, it could be a substorm that's east or west off that line, so reaction is going to be is going to look a little different. And it's going to eventually come to me, because if it starts somewhere here, if the onset is again, I'm post midnight and it's a pre-midnight onset, eventually it's going to trickle to me at some point, because that's what happens with substorm current wedge. They start in one point and they spread in all directions, but that spread kind of depends on the substorm, so it may not be even. But it may not come. It may be a small thing, and I could be sitting there and waiting for nothing. So again, location, time, and smaller stuff may not necessarily be detected if it's, well, I'm not going to be looking for it if I'm sitting close to Minneapolis and there is a substorm somewhere in this area. I'm going to have trouble catching it, but I'm not going to know until I actually see the signature in magnetometers. And again, I have to wait for full expansion to say, well, yeah, that was a good substorm. So maybe not. And again, not everybody is as lucky as we are, where we do have that line that literally is sitting at my longitude, and it can show me exactly what's happening at that longitude. And this is what you can see. This is, again, for us, this is pre-midnight, way pre-midnight. And you can see that you have negative deflection here, positive deflection here. So interpreting that is a little bit difficult. And there's still a substorm happening, but is it a substorm that happened at a different point, that started at a different point? Oh, I know for sure it did, because this is nowhere near close to my magnetic midnight. And it spread to me in that westward flow. So it might have lost some strength along the way, and probably Aurora is already going by the time I'm starting to pick up signature. So the full sort of magnetic signature in magnetometers is always behind what Aurora is doing. That's normal, that's expected. So if you are eastward or westward of the onset, expect some delays in both aurora arrival and to see the signature in magnetometers. And you're not going to know how far it extended. Is it actually just in that line? Is it spread further west, east? And yeah, that creates some complications. So next step, let's go with magnetometer network. Now we're going to cover everything. Look at those beautiful magnetometers. Well, some of them are not in real time. So good luck getting that data.
Oh
They
boy.
don't report in real time. It's going to come up to you. It's going to be available through one of the big databases. 2, 3 days, maybe even later. Is it good for you in real time? Also, look at all of that complexity. So you see a couple of magnetometer lines. Let's just pretend a substorm happened. This is a pre-midnight, so it's 5 UTC, which is 2300 hour local time, or about. So the substorm onset is here. So I'm going to be seeing it, but who else might be able to see it? Well, Alberta, possibly further in Canada, maybe Greenland. I don't know. You're going to have to look at magnetometers to see what they're doing at those longitudes and latitudes. So we're just raking up complexity like there's no tomorrow. It's nice, but you're going to have to look at several stack plots to kind of figure out, and you have to remember the latitude of all the different magnetometers. You have to do complex calculations of just where that substorm onset was. Guess what? I would rather the Glendale app do that for me.
I was waiting for this.
Because that's exactly what the Glendale app is doing. It's looking at the network of magnetometers. It is figuring out just how strong that substorm is. It can tell you the latitude of where things are happening. And all you have to figure out based on the strength, whether or not that strength would be sufficient for you. Again, one of the limitations is you have to remember that if you wait for full expansion, you're already too late to the best part. So that's going to be a limitation of any app that's using magnetometer data. But the Glendale app can has a feature that can help you overcome it. It can tell you the next substorm. So it does have a loading unloading feature that predicts with fair degree of accuracy when the next substorm is going to happen. It is set up to predict it on earlier time. So you can wait and it sort of tells you if it's going to be minor, if it's going to be moderate, if it's going to be strong activity. The more time you spend with it, the better you might be able to predict just how big that next substorm will be, depending on what magnetosphere is already doing and how solar wind will affect it. So depending on BZ, you can tell to some degree when it might happen and how big it's going to be. And the app's definitely going to help you in that regard. So that's kind of it for magnetometers, actually. So that's a lot of slides, but
Well, time too.
I like
Dang,
how
this is gonna be a
I
good
like how
one.
you wrapped it all up with, the Glendale app does this for you.
Glendale does it all for you. You don't have to worry about any of this. Just look at the
yeah,
substorm strength.
Or
correct. Or better yet, look at when the next activity is coming. It may not be predicting sawtooth events, or if it's stuck in SMC, it's going to try to predict when we're going to get out of SMC, where there's just that kind of green glow on the horizon and not a whole lot of happening because there is no substorm. It's all
right.
just going there. It's circulating, it's convecting. There's a little bit of aurora going on, but there's no release. There's no big explosion. So Glendale app is trying to predict when it's going to happen. So it looks at certain features in the solar wind, like BZ flip, to tell you that, oh, it's coming. So be ready, be prepared. There is I think a feature in beta testing for the sawtooth events, but they're about 3.5 hours, technically 2 to 4 hours, but not bad.
Yeah.
It can
So
tell you a lot. And you start to kind of see it in the solar wind data. So if you know what kind of solar wind would be helpful for your location, what magnetosphere is already doing is it sort of suspended in that convection, and the change in the solar wind either get that convection stronger, so it will build up to a substorm, or it's going to break the SMC with a negative BZ. You're in good, you're in good shape.
done. It's like you said, it gets complicated very quickly, but it's nice to know some of the reasoning behind these things. So like when you look at an app like Glendale and you can sort of understand how it's functioning, it just gives that little bit of insight. And then if you want to play around with it, then you can look at magnetometer data and see how well you can interpret it, which is fun to do. But it's pretty crazy how much you could get information from that. Like these things, they tell you a lot. So it's pretty fascinating. So thanks for
Yeah,
that.
they certainly do. And the TGO, we can probably put a link to it that can put things into perspective. So you start to see, you can look how the night went. For example, if you wake up in the morning and kind of look at the line, that's super helpful.
Yeah.
The issue for Southern Hemisphere that we deal with is First of all, there are not a few, there are very few magnetometers there because there's not a lot of land there. So there's just not many places you can stick magnetometer. And the currents that are responsible for aurora and are responsible for substorms are actually weaker in the southern hemisphere. It's not entirely clear why they are, so substorms still happen, but the magnetometers are having sort of lukewarm response to it, except during summer.
Oh,
So when it's summer, and summer, it's sort of summer months in northern hemisphere. That's summer, technically.
yeah.
Um, so that's not, we're not quite there yet. Um, but you can rely on other magnetometers because of the magnetic conjugacy. So to some degree, you can look at the northern hemisphere magnetometers and see what they're doing to see when substorm is going to happen. Again, not a whole lot of magnetometers. You probably have to knock on the door, um, on the Russian door and say, can we use your magnetometers? Because in the network, those are the magnetic conjugates. So they're sitting on the same longitudinal line. Do you want to do it? Probably not. Do you have to do it? No, because by figuring out how things work in the network of magnetometers, you can figure out when substorm is going to drop, and you can detect it in other magnetometers and extrapolate it for sort of magnetometer deserts. And that's exactly what the Glendale is doing too.
Oh, that's
So
good.
it's pretty cool.
Absolutely. Well, thanks for that primer on magnetometers.
Well, like a crash course.
Yeah, crash course.
That was
Crash
a
course.
pretty dense crash course too. It had all the information I really needed in it. With I'm surprised you got through it in time too. I would have taken probably an hour to go over all that.
I know it was like 8:33. I was like,
So props
dang.
pushing it together. That is.
Well, that's fun.
Yeah.
Well,
Maybe this will be part one in a series or something.
yeah, I mean, it very well could be because
It could be because we kind of
it,
move toward the magnetosphere land, so we can look at a couple of magnetospheric modes, which would be helpful. We kind of covered them
yeah,
previously, but it's good to have a
Yeah, I
refresher
can always go back.
and
yeah,
sort of
yeah.
say, well, this is what we see in magnetometers.
Mm-hmm. I dig it. Well, yeah, well, let's see. So next week we have our guest on. So we'll be doing
Yes,
our guest.
Sarah.
Yay!
Next Saturday,
Uh,
8 p.m. Eastern.
yeah, so we will be doing that.
I want to
But
hear her
we'll
rant.
figure out. Yeah, I do too. She's a character, I like her. But then we'll figure out what kind of topic to cover next. So hopefully, it never ends. We can talk about space weather forever and ever.
And we can always go back and repeat things differently. I mean,
Oh, for
it's
sure.
not like we can't revisit old topics if we need to.
Yeah, that's good. So good.
Or
It looks like
we may get some sun activity finally.
finally, and then maybe we could just do an impromptu one, like a fun little let's tear this apart type deal.
I
So
hope.
let's hope for some activity. That's what we'll hope anyway.
Yep.
Well, it looks like a couple people picked up some little tidbits information out.
Yay!
Hey, good. Our job is done. So we will let you go.
Haha.
I'll play with my slinky one more time. But
And
we'll let you go. Have your
I
evening.
can probably put the slide. If anybody, so Margaret and Les, if you want any of the slides, let us know. It
Yeah.
might be helpful.
Yeah, we can definitely hook you up with some of those, especially some of the I guess more pertinent slides like on how to read it or something like that. Or we should just give them that complicated picture just to post. Like, this is what we went over in a
Scare
half hour.
everybody away from magnetometers.
Yeah. All this is what we went over. It's a mess. Well, anyway, we'll let you guys have your evening back. And thanks for joining. We always love having you here. And we'll keep this thing rolling. So good night.